So now in the last lecture we have learned to derive the equations of motion using the graphical method, and this method we use when the motion of the object is in a uniformly accelerated motion. But there's another method which we can use to derive the equations of motion for non-uniform accelerated motion, and that method is called the method of calculus. Now we have defined instantaneous velocity before. The instantaneous velocity is defined as the limit of the average velocity which is delta x by delta t as the time interval tends to 0. So this is the instantaneous velocity, and this is equal to ddt of x. So this method is known as differential calculus. Okay, we have the instantaneous velocity to be equal to dt of x, or dx by dt. Now to understand this method, what we'll have to do is we'll have to to understand this method, we'll have to plot a graph between the position and time, or we just draw the position time graph. For simplicity, we'll take a uniform motion. So here we have the position and this is the time graph. So for simplicity, we'll take the uniform motion. So this is a uniform motion. It means that the velocity here is constant. So the particle moves from the initial position, which is at 0, to the final position, which is at say, I'll write x only here, so x, and the time it takes to cover the distance x is, say, capital T. So this is the position time graph of a uniform motion. Remember, here the velocity is constant. So how do we define this instantaneous velocity? V, this is equal to, we have dx by dt. Now in this case you see the time interval is from 0 to t. But on defining this instantaneous velocity, alright, this time interval has to be very small. See, if we define average velocity, you just need to know the time interval 0 to t, and the distance move is this one, 0 to x. So you just need x by t, that will give you the average velocity. But if you want to find the instantaneous velocity, the time interval, this time interval has to be very small. So this dt here, this is very small, and this has to be, this time interval has to be divided into very, very small parts, which is dt itself. So you divide this into very small equal parts, and these small equal parts okay, so we divide the time interval from 0 to t to small intervals. These intervals from here to here, from here to here, from here to here, this interval, they are equal, and these intervals can be taken as a dt. Okay, so here this dt, this interval is very small, and it tends to 0. So for this dt, what will be your displacement? For this dt here, the displacement will be this one. So here this is your dx. Then from this one dt, this is also dt. Then the displacement will be again dx. Then for this interval here, the displacement will be this, and for this interval here, the displacement will be this one, and for this interval here, the displacement will be this. So you can see here, these dx, they are these small displacement. So here for dt tends to 0, this dx also is very small. So as you can see here, we have divided them into smaller parts. You divide the time interval into smaller parts, then your dx also will be divided into smaller parts. So if you have to take v dx, this instantaneous velocity, you'll have to divide this one dx by this, and here also you'll have to divide this dx by dt, and here also this is your dx by dt. Here also dx is this one, and this is dt, and here also this is dx and this is dt. Remember that the time interval here dt is very, very small, that is tends to 0. So here you can see in the differentiation, in differential calculus, we are dividing them into smaller parts. Okay. And if I draw the velocity time graph of this motion, and since it is a uniform motion, so if I draw this velocity time graph, so t, so this is the velocity time graph. Now since it is a uniform motion, it moves with a constant velocity. Say any velocity with a constant c, denoted by constant c. So that will be the velocity by which the object is moving from this interval 0 to t. So in this interval 0 to t, the object moves with a constant velocity. Again here also, if you can recall, the area under this area under the velocity curve will give us the displacement, that is x. So if you want to find this x, we'll have from this velocity time graph, we'll have to find the area under this velocity time graph. And by using this method, what we'll have to do here also, we'll have to divide this t into smaller parts. So I'll divide them into smaller parts. So here is your dt. So dt, 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 dt. So if you add all the dt, you will get this time interval t. Okay, so here these are your dt, but what about your v? Your v is constant. See, your v doesn't change. In here you can see that when you change dt, this dx also change. But here, okay, there's a small change in dx from here to here. This is dx, a small change. From here to here, there's a small change. But since this is constant, the velocity is same. It does not change. So here, what we'll do is this. We'll use this formula. From this formula, we have by cross multiplication v dt. This is equal to dx. Okay. And since this velocity is constant, is equal to c. So I can write this as c. Remember, c is the velocity. Okay, so c is the constant velocity. dt is equal to dx. And what is this dx? These are the small increment in the displacement. dt is the small interval. dx is the small increment. After every dt, the increment is dx. So if I want to find this 0 to x, what I'll do is I'll have to sum all these dx. Okay, so here these are dx, right? So if I want to find this x, I have to add this. Means I'll have to sum all these small dx. And that summation is called integration. What I'll do here is I'll integrate. So this is a symbol of integration. If I integrate in this side, I should also integrate in this side. So if I integrate this dx, these dx, then I'll get the displacement x. So again here you see that if you integrate this, you'll get the displacement. So here integration, or it is called summation. Okay, it means a summation, but it is called integration. Okay, so if I integrate this, then I'll get the displacement x. Okay, so sum all these dx, 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 you will get what? X, the displacement. So here the displacement is equal to integration c dt. Now we never integrate this c is a constant. If it's a constant, then you'll have to keep it outside of the integration. So here integration of t, again here means you have to sum all these dt, 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 dt. Here also you see dt, 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 dt. You sum all these dt's. You will get what? The time interval. So here integration of dt, this will give you the capital T. Okay, so here ct is equal to x, the displacement, which we have done in the last lecture. C into t would give us the displacement. So this is a simple case of uniform motion. We can have a non-uniform motion also. We can use the same method, and the velocity, since for a non-uniform motion is not constant, so we'll have to take into account the how to integrate the velocity also. Okay, so now let us use the method of calculus to find the equations of motion for a uniformly accelerated motion. Since it is an accelerated motion, okay, the motion is non-uniform. Okay, don't be confused with non-uniform motion and uniformly accelerated motion. Okay, if there's acceleration, then the motion is non-uniform. But if the change in velocity in each interval is the same, then it is called a uniformly accelerated motion. And we have done this uniform accelerated motion before, and the velocity time graph of this uniformly accelerated motion is drawn in this way, where this v0 is the initial velocity, that is at time is equal to 0, the velocity is v0, and at this time t, the velocity is v. So to use a method of calculus, what we'll have to do? We'll have to divide all these dt. Okay, we'll have to divide this time interval from 0 to t into smaller time intervals dt. So we have dt here, and then this also dt, and this also dt, and this also dt. Okay, I'll just bring this one close, so that will be equal, and this was also t. So these are the small time intervals dt. This is your dt, 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 dt. And look at the velocity also. Since this is not a constant velocity, the velocity also changes. So we have small dv there, here also dv, here also dv, and here also dv. So these are your dv's. So we have the first one, v, dv, 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 dv. So these are the different time intervals, and these are the different velocity, change in velocity. So in this time interval, there is an increment dv. So this, I'll take this as dv. So from here to here, the change in velocity is dv. So in dt, the change is dv. Okay, there's an increment after each time interval. There is an increment. So in this interval, there is an increment dv, dv, dv till you reach v. So here, the instantaneous acceleration, we have defined this one before as dv by dt, and our aim here is to find the total time, the equation of motion, by using this method of calculus. So what we'll do here is, Upon cross multiplication, we'll have a dt dv. Then remember, the acceleration is uniform, so it is constant. Okay, your acceleration is constant for this velocity time graph. So just like we've done earlier, what we'll do is, if you want to find this velocity, total velocity from v0 to v, or the total time interval, what we'll have to do is we'll have to integrate. So upon integrating both sides, if I integrate both sides, I'll write first this dv here and a dt. So if I integrate this, I'll get this. Okay, so this is how much? From here to here it's v, from here to here it's v0, so this is v minus v0. So what I'll do is I'll integrate from v0, starting from here, to v. Alright, if I start from 0, I'll get v. But if I start this from v0, then v. So I'll sum only this part from here to here. I sum only this. So for this one also, integration, I sum starting from 0, integrate from 0 to t. So integration from 0 to t will have a dt. So again here, if you sum all dv, what you'll get is v. But since you have the limits, you write as v, then we have the limits. v0, I'll write it here, and v. So this is a mathematical step, a mathematical step. And here also, a is constant. Remember, when you have constant, you don't take the integration, so you take the integration out. I mean the acceleration outside of the integration. So you have a dt, then from 0 to t. Again here also, if you sum all the dt, what you get is the time interval t. And here I have to integrate from 0 to t. So I'll have to put the limits. When you have the limits, you'll have to put the limits also. So I'll get t, but within the limit 0 to t. The next step is to put the limits. Now in this case, what we'll do is we'll have to put first the upper limit, which is v, then we have to subtract the lower limit v0. So we have to subtract this v0 from this upper limit. So what I'll do here is, if you put first the upper limit, which is v, and minus the lower limit. So this is again is a mathematical step. Okay, so this is a method which you use in integration. Then again here also, what I'll do is I'll put first t minus 0. What I'll get is t itself. So I'll put first the upper limit t, then lower limit 0. Okay, so always upper limit minus lower limit. So here t minus 0, which is t. So this will be the first equation of motion by using the method of calculus. So we have derived this first equation of motion by using method of calculus. Next is to derive the second equation of motion using this method of calculus. In the second equation of motion, what we need to find is the displacement, okay, from this interval to this interval. And let us say at 0, the position of the object is x0. So or this also, you can bring this v0 this side, we'll get v. So v is equal to v0 plus at. If you bring this side, it becomes positive. This is the first equation. So now from the instantaneous velocity, v is equal to dx dt by dt. And again here also on cross multiplication, we have v dt. This is equal to dx. So if I want to find the displacement, I have to integrate it. So integrate both sides. So what I'll do here is I'll integrate dx. Okay, I'll write first dx, integration dx. Now at t is equal to 0, okay, I'll put this one also, v dt, so integration both sides. Now at t is equal to 0, x, the position is at x0, and at time is equal to t, the position is at x. So we'll have to integrate within these limits, x0 to x, 0 to t. time is equal to 0, the initial position is x naught. At some interval of time t, the position is x. So we'll integrate this one, and here v is not constant like in the earlier case. Your v is constant. So like in the other case, the velocity is constant. So here, since the velocity is not constant, we'll have to put this one. V is equal to v naught plus at. So I'll put this one here. And integration of dx, what will give you integration of dx? Integration of these dx, I do not draw the position time graph here, so this will give you x. But we have a limit, so we'll write x naught. So we'll write x naught, x. Then integration of this. Now v is how much? I'll have to write v naught plus at dt. Okay. Then this one too we have found out. This will be putting upper limit minus lower limit. X minus x naught. And this what we'll do is we'll put dt here first. So integration 0 to t v naught dt plus integration 0 to t at dt. So here this v naught, this is the initial So here this v naught, this is the initial velocity, it has a constant value. So this v naught will be taken outside of the integration. And acceleration for uniformly accelerated motion, this is constant, so you take it outside the integration. So here integration of dt will give you the total time t. This will give you t within the limit 0 to t, and again you have to put the upper limit minus lower limit. T minus 0 will give you t itself, so here we'll have v naught t. V naught t. Now in this case, since we have t dt, we have to use a formula. Okay, it's given the mathematical formula. So this is the mathematical formula. Integration of t to the power n dt. Okay, now this n is an integer or a number. It can be 1, 2, 3, 4. So here we have integration t n dt. This will give you t to the power n plus 1 divided by n plus 1. Okay, so integration of this will give you t to the power n plus 1 divided by n plus 1. So here what we'll do, integration t dt. What is the n here? 1. So if I keep here n to be equal to 1, then this will be 1, and this will be, remember this formula, right? 1. So that will have 1 plus 1, this will be 2, and here also 2. Okay, so integration of this t dt, this one will give you t square by 2, and if you put again the upper limit minus the lower limit, you'll get this one, t square by 2 minus 0. So we put this limit, if we put with this limit 0 to t, we'll have to take t minus 0, which is this itself. So the integration of this will be t square by 2. T square by 2. And this is the second equation of motion. So we have here plus, and right here half at square. So this is by using method of calculus. We have derived this a second equation of motion. Okay, so you have to remember this formula. Integration of t to the power n is integration of t to the power n dt will be t to the power n plus 1 divided by n plus 1. Remember this formula. Next is to derive the third equation of motion. So what we'll do here is, again, your instantaneous acceleration, this is equal to dv dt. Then I can write this one as dv, so I can write this as dv by dx, but I'll write here dx also, dx dt. So this dx cancel to get dv by dt. Okay, so you can cancel dx and dx. What you'll get? dv by dt, which is same. So here, this dx by dt, this is the instantaneous velocity, isn't it? So this one, you can write it as v. So hence we are eliminating this dt. So to get a to be equal to dv by dx into v. Then again this will come here. So a dx, this is equal to v dv. So again what I'll do is I'll integrate on both sides. So integration on both sides from the limit, in this case we are integrating over this dx, so from the limit x0 to x, and integration we're integrating this with respect to this dv with respect to the velocity. So here we have initial velocity and the final velocity. So at x0 the initial velocity is v0, at x the final velocity is v. So here again a is constant, so we take it outside of the integration. Then again we have again this same here, integration of dx within the limit x minus x0, and this we have done. This will give us x minus x0. Now v dv, we have to use the same formula of this integration of, here instead of t we have v, okay, but the same formula applies. So in general the formula is like this: integration x dx for any variable, okay, it can be t, it can be x, it can be v, okay, it can be any variable. So this will give you x n plus 1 divided by n plus 1. So this is the general formula for any variable. So here we have v. So what we have here is, so here instead of this variable x, I'll write v. Here also I'll write v. Here also I'll put v. Here also n plus 1. So here v will give you, since this is 1, so we have 1 plus 1, and again it will give you v square by 2. So I'll write here v square by 2 within the limit v0 v. What I'll have to do with these limits, I'll put first the upper limit, then minus the lower limit. So what I'll get here is upper limit v square, put it here, minus lower limit, put it here, v0 square divided by 2. So this is the third equation of motion. If you bring this on the side, you'll get 2, and that will give you the third equation of motion. So this is by method of calculus.